This split screen highlights the difference between a chatbot and an agent. On the left, we see a model generating lines of text in a static window. On the right, we see a back-end script executing a chain of commands, connecting to a server, querying a database, and outputting a specific calculation. The shift from generating text to executing independent actions marks the transition into autonomous systems. We are no longer just asking a model to describe a solution. We are building a model that implements it. Traditional software relies on rigid if-else logic. These systems function like a set recipe, effective for predictable inputs, but prone to failure the moment they encounter an edge case the developer didn't anticipate. Machine learning solved this rigidity by using statistical patterns to handle unstructured data. However, these systems require constant manual retraining to remain accurate as the underlying data shifts. Agentic architecture combines these approaches. It uses probabilistic reasoning to understand a request, but relies on deterministic code to execute the task. While AI models are powerful, they cannot interface with a file system or a cloud server on their own. They produce text. It is the engineer's role to build the infrastructure that interprets that text as a system command. Deploying enterprise AI requires constructing this environment layer by layer, moving from the base transformer model to a scaled multi-agent system. The foundational unit of this system is the large language model. At its core, an LLM is a transformer architecture designed for a singular mathematical task, predicting the most likely next token in a sequence. Models do not process English words as a human does. They process tokens, which are mathematical groupings of characters. A common word might be one token, while a rare or technical term is broken into several. The LLM ingests tokens, calculating probability for the next block. We control this with temperature. Low temperature collapses the tree to the highest probability path. High temperature explores lower probability paths. Lastly, a context window limits memory. As data advances, older tokens falling outside are permanently removed. Simply expanding this window does not lead to better performance. As the volume of data increases, the model's ability to pinpoint specific facts degrades, often leading it to pull incorrect information from the noise. Even with a massive context window, the model remains isolated, no access to live internet, cannot check the current time, and cannot interact with external files. In this state, an LLM is a theoretical engine. To perform actual work, it must be wrapped in an execution framework that provides a bridge to the external world. We bridge this gap using the React pattern, reasoning and acting. This architectural structure forces the model to document its thinking before it is permitted to execute a command. This creates a continuous feedback loop. Observe, reason, act, and evaluate. The act phase is powered by tools. Here, the LLM passes a specific instruction down a wire into a secondary module, containing external APIs and functions. Tools are deterministic software wrappers, functions written in Python or JavaScript that do exactly what the model requests. They provide a predictable environment for the model to interact with. This is mandatory for precision logic. If you ask an LLM to calculate 60 seconds from now, it uses probability to guess. An engineered tool uses code to calculate the exact timestamp mathematically. The tool executes the specific task and feeds the concrete, non-probabilistic result back into the model's observation loop, providing it with a factual basis for its next move. Without tools, the model cannot influence an external system. These engineered functions provide the only available bridge between raw prediction and actual work. Despite these tools, the model still suffers from amnesia. It starts every new API call with a blank slate, having no memory of previous interactions or private company data. Retraining the base model on your private data is both expensive and insecure. Once data is baked into the model's weights, it cannot be easily updated or removed. The modern solution is a vector database. It converts text into arrays of numbers, called vectors, plotting them in a 3D grid based on meaning. This grouping enables meaning-based search. A dot product calculation between a new query and existing coordinates instantly locates the relevant cluster. We connect this database to the model using Retrieval Augmented Generation, or RAG. In a RAG pipeline, the system intercepts a query, retrieves the relevant vectors from the database, extracts the original text, and injects it directly into the LLM's context window as a reference. This requires precise engineering to determine how much context to provide. Too little leaves the model uninformed. Too much creates noise that leads to hallucination. RAG provides a private, up-to-date brain for the agent, allowing it to reference internal documents without requiring a single cycle of model retraining. As an agent's capabilities grow, the technical debt of maintaining it grows as well. If an engineer writes a custom API wrapper for every app, the system becomes a tangle of fragile, unique connections. To solve this, the industry is moving toward the Model Context Protocol, or MCP. MCP acts as a universal adapter, replacing custom connectors with a single, standardized conduit that allows communication with any external application. This standardizes exactly how permissions are handled. It allows the engineer to dictate exactly what an agent can read or write across the entire ecosystem through a single security layer. By adopting MCP, engineers can scale agent connections without reinventing the communication layer for every new tool. When we combine the React loop, tool execution, and RAG memory into one system, we arrive at a smart agent architecture. For complex workflows, we scale this into a multi-agent system. In this hierarchy, a manager agent analyzes the goal and spins up specialized worker agents, each with its own tools and memory to execute subtasks in parallel. This parallelism comes with a significant cost. Every active agent consumes API tokens. A single complex request across 20 subagents can consume a week's worth of tokens in seconds. Cost optimization is essential. Engineers route simple formatting tasks to lightweight, inexpensive models, reserving the most advanced models strictly for the high-level reasoning and planning phases. Autonomy introduces risk. Operating on probability, models can execute unauthorized commands if prompt logic is bypassed. To prevent this, safety guardrails are implemented. This middleware layer intercepts all inputs and outputs, validating commands against strict security rules before they reach the model. We also use sandboxing to isolate the environment. This ensures that even if a model generates a command to delete a system file, that command is trapped in a safe, disposable container where it cannot cause damage. Deploying enterprise-grade agents necessitates the construction of these deterministic shells. The value of the system lies in the software engineering that wraps and regulates the model's probabilistic core.